All right. Before we get started, does anyone here speak French? Just one? I recently learned that roughly half of the English language comes from French. Have you encountered like vast similarities in the vocabs?
They're very similar.
Yeah. Well, that's actually an interesting point that I want to make. The 19th century French writer Alexandre Dumas was actually learning English himself, and he was looking at an English book, and he read it, and he noticed all the similarities between the two languages, and he remarked something. This is probably apocryphal, but he remarked that English is all French, just badly pronounced. So with that, I think functional programming patterns are kind of interesting because you can find them in some unexpected places. And as Dumas found with his French vocabulary, we will find that recognizing functional patterns in unfamiliar systems like radios can actually help us understand them. And in this talk, we're going to use our knowledge of functional programming to reason about digital signal processing systems by essentially looking at them through the lens of category theory. So before we jump into the theory and playing with the radio, I want to show you just sort of a simple technique, a very informal technique. It's like a huge disclaimer for visualizing categories and thinking about them, which I like to use because it helps me think about how their meaning applies to functional programming. And then we'll jump into three basic concepts from category theory: composition, functors, and natural transformations. For each one of these, we'll start with a theory. We'll do a really brief introduction to the category theory. We're not going to go deep into that. And then we will look at a familiar example of that from functional programming and then see what that can teach us about digital signal processing. Okay, so let's jump right into that. So a category, I like to think of a category like this. It's a box with a name, and it has two sets of things in it. It has a collection of objects, X, Y, Z in this example, and a collection of arrows which go between objects. So in the category C that we've drawn, we have the objects X, Y, Z, and we have two arrows, one from X to Y and one from Y to Z. Categories have some other things like the composition operator, which we'll actually get to later, as well as things that we won't get to, like identity arrow, various laws, and so forth. As I said, this is a very informal tool that at least the way we will use it today. In functional programming, we often use the category of types to reason about our programs. And the category of types has, for its objects, just simple types, string, int. If you have a class user, user could be a type in your category. And the arrows in this category are well, often, and in the example we're using, arrows are function types. And so they go between the simple types in our category. I've also seen the category of types use functions themselves rather than function types as the arrows. And I've also seen the arrows represent sort of families of functions. So if we look at int to string and think of that sort of representative of every possible function into string. But this category is useful in functional programming because it helps us reason about the domain of possible types of our programs. Basically, everything has to fit into what's in this box. In functional programming, well, I guess statically typed functional programming, we often, in addition to the category of types, we also often treat type constructors as categories. So in this case, where we had just regular old types before, we are representing the option type constructor as a category. So objects are concrete instances of option of something. And again, arrows are just between those types. And so just for another example, here's the list category, and it's the same type of thing. So our objects are concrete lists. We chose A and B here, but it could be int and string or whatever types you like. And again, the arrows in this category go between those objects. Okay, so before we talk about categories of the radio, let's actually look at the radio and see what we're working with. So we have a couple things going on here. We have a transmitter, which is a HackRF1 that we'll be using to send out a signal shortly here. And this is a software-defined radio. So the sort of short version is software-defined radio is a piece of hardware that puts as much of the radio logic into software that's running on the computer as possible. So all of your mixers and amplifiers and modulators and filters and all that stuff is implemented using some type of software. And then the hardware is as minimal as possible. It's in the ideal situation, it's just a digital to analog converter with an antenna stuck on it. In practice, there's a few other things. There's a oscillator for the carrier frequency and some other stuff. You don't need to memorize any of this, just hopefully find it interesting. The software we're going to use to transmit is GNU Radio, and we'll get into that in a second, but it looks sort of like this. It lets us build up software radios as these flow graphs of blocks that operate on signals. To receive our signal, we're going to use an RTL SDR. This is a super inexpensive piece of hardware you can pick up for 15 or 20 bucks that was originally created for receiving digital TV. So if you wanted to get TV on your computer, you just buy one of these. Until someone figured out that they're actually implemented as a software-defined radio. So somebody wrote up some drivers for this thing, and now you can actually use it as an arbitrary radio for receiving transponder signals from airplanes, or you can make a police scanner out of it, or there's all kinds of interesting applications. If you just search RTL SDR, you'll find all kinds of hobby web pages and things. That is plugged into our receiver software, which you saw when you first came in. This is a program called GQRX, and it's really just a software-defined radio receiver program. So we're going to use this to look at the spectrum of signals that we're receiving and see them change over time in that waterfall diagram. And finally, our last piece of hardware is this cheap handheld transceiver, and we'll be able to actually hear the signal on this, so that you, since we're using one computer for the SDR, this sort of proves that it's real. Okay, so let's jump into the radio itself. I don't think there's a way to zoom, so but that's okay. The thing to get out of this is GNU Radio. This is actually called GNU Radio Companion. It's a graphical tool that sits on top of GNU Radio, which is itself a suite of signal processing tools that are generally used to make radios or audio algorithms, things like that. In our case, we have a very simple radio. It's got 5 blocks and connections in between them. The blocks represent some operation to perform on an input signal. And then the lines between them they're almost like wires. You think of the signal traveling through that wire. And the whole thing flows left to right. So it starts with a source block. And this block is producing our source signal that we want to transmit. In our case, it's a simple Morse code signal. That signal is then fed to an amplifier, which reduces the amplitude of the signal by half, just so we don't need to transmit very much power for this demo. So that kind of reduces the power. That amplified signal is then passed to a modulator block, and that's where we take our raw continuous wave and modulate it using narrowband FM, which typically is not done for Morse code, but for the sake of a demo, it's really good because then we can receive it on this thing, which makes it much more fun. And then finally, the signal is filtered. So before we transmit, we want to make sure that there's no spurious signals or high-frequency components or aliasing or any kind of dirtiness that we don't want to transmit. We get that out with a filter. And then finally, we dump it into a sink, which transmits using the HackRF. So let's actually run this. Actually, before I... So that was greetings from LambdaConf, and then my amateur radio call sign. So I had to change the tuning of this while that was transmitting. We're broadcasting on 430 megahertz, which is an amateur radio band frequency that this thing supports. It is a licensed band, so when you transmit, you have to send out your call sign, and there are certain rules to abide by. Okay, so the radio works, woohoo. So a flow graph is composed of blocks and connections, but we can actually think of this as a category in which blocks are the arrows and connections or signals are the objects. So in this block diagram, we can just think of blocks as arrows between signal objects or operations that operate on signals. Okay, so that was visualizing categories. I should probably, there we go, way more professional. Really the takeaway here is that categories, especially if used informally, can be used to visualize anything you like. So in this case, we visualized a flow graph as a category, and we also saw the category of types and a sort of unspecified category C. So let's jump into our first category theoretical concept, and that's composition. So in category theory, a category is composed of objects and arrows, as we said, but it also has a composition operator. Its job is to assemble pairs of arrows as long as the types line up. So for example, if we have our category from before with arrows x to y and y to z, we can create this composite arrow x to z by composing y to z with x to y. And notice how the order seems kind of reversed here, because our final arrow goes from x to z, and the arguments, I guess the arrow that processes that x is the second argument to the composition operator, which spits out a y. That y is fed to this arrow, which spits out our z. So just kind of make a mental note. In practice, if you were to evaluate this compound arrow, the second argument is what runs first. So it takes the x input, passes the output to the next arrow. In functional programming, we have various ways of doing function composition. Haskell has the dot operator, which we see here. Scala has the and then and compose methods. These are methods on the function object, and you'll notice that the arguments are switched on these two. So and then says, I have the sort of first stage of my compound arrow, and I'm passing as an argument the second stage. Composes the reverse direction. You start with the sort of secondary and compose it with what needs to happen first. And all of these are just equivalent to a simple lambda that, given an x, evaluates m with the x, passes the output to n, and then passes the output out of the lambda. Oh, and by the way, since we do have sort of different sections that we're going to do composition, functors, natural transformations, and we're like jumping back and forth between radios and stuff, please interrupt me with any questions, or if you want to know how something works or dive into more detail, I'm totally happy to do that. Okay, so let's go back to the radio. And our radio is actually using composition. If we drill down into this block, for example, this is our Morse code source. We can see that it's actually made from several lower level blocks. And you don't need to understand these other than to realize that we need to put all of these together to get our source signal. For example, we have our original Morse code input. We have a way to extend it so it's a longer signal in time. Then we have to mix it with another signal that will give us our tone, and et cetera, et cetera. But when we're dealing with our radio, we don't want to think about all this stuff. So we create this kind of abstraction of all of these things and call it just the source. And to do that, we're using composition. And we'll see the same thing for the filter block and the transmitter if we were to drill down into those as well. So the way this works, I'm going to make this bigger, is imagine that we have two low-level blocks M and N, and we don't want to see them. We want to abstract them as just a single M and then N block. So in GNU Radio, it's pretty simple. We're just wiring them directly together and then abstracting them as a hierarchical block. But internally, M and then N is N compose M. And so maybe even without knowing it, we were using composition to build that block. So pretty simple, but the interesting takeaway, I think, is that composition is actually pretty useful for hiding complexity by abstracting. And in our case, we didn't just abstract two functions as one. We have kind of many levels of composition happening to turn these 1, 2, 3, 4, 5, 6 blocks into a single block. All right, so now let's talk about functors. Okay, so in category theory, a functor is a mapping between categories. And what that means is it provides a way to take objects and arrows from one category to another category. So here we have actually three categories: category C, category D, and the category of functors. We have one functor, which is an object in the category of functors. And it is a functor from C to D. And that's kind of how we would read all of this. So a functor provides a mapping between categories. So first, it provides a mapping of objects. So if we wanted to pull that A into the D category, we could use the functor f to create an f of A that is a D object. And similarly, we can use a functor to take an arrow from C, so A to B in this example, and pull it into D as an arrow f of A to f of B. And the reason it might be maybe unfamiliar to you that the D object and D arrow are f of A rather than D of A, like if you were thinking of D as a type constructor. And that's just because category theory is more general, and in functional programming, usually the functor and the type constructor have the same name. So a concrete example would be, again, going back to our categories that we saw before, if we have the category of types and the category of the type constructor option, and we introduce, we want to map between them. Actually, in practice, we don't use a functor to map objects between categories in functional programming. We use type constructors. So for example, the mapping between types and option for int is the type constructor option. Arrows, on the other hand, do use functors. So in functional programming, if we have a function int to string and we want to map that into the option category, for example, maybe we have an option of int that we need to apply that function to. That's where our option functor comes into play. So what we're looking at here, just like before, is three categories. Our third category, functors, has objects that are functors. And here f is a mapping between the category of types and the category of the option type constructor. This is usually implemented as a type class. If you work in Haskell or if you've used Scala Z or CATS, you've probably seen this. But you can see that it has the same shape as our arrow on that previous slide. We have an A to B that was like our int to string. And mapping that function converts it into an arrow, essentially f of A to f of B. And then, so here's an example. If we were to implement a functor for the option type, given a function A to B and an option to maybe apply it to, we either produce a none or a sum that we've run that function on. Scala is also an object-oriented language, so we often also see this pattern where this mapping is not really in a functor type class. It's more of almost like a mappable trait. So anything that's sort of mappable will define map in this way, where we still have our A to B, and that was like our int to string. And when we map that function, we get our option of A to option of B from the trait itself. This could also be implemented in these two implementations. Okay, so let's find a functor in our radio. If we go back to the radio and look, actually, this is a little easier to see. If we look at this amplification block, it starts to get interesting. So this whole radio, everything we're looking at is dealing in signals over time. So a signal in digital signal processing is just a series of sampled values over time. And then those streams of values are flowing through each of these blocks. And a signal over time in DSP is commonly referred to as a time domain signal. But the interesting thing about amplification is all it's doing is multiplying the value of each sample by 0.5 in this case. And multiplication has nothing to do with time domain signals. It's just give me a number and I'll give you another number. So this is actually, we can think of this as a functor. So if we have a function, sorry, I'm getting a little ahead of myself. So if we think of the time domain as a function that varies over time, like for example, we could have a source signal that's just sine of t, where t is time. And we have an amplify function which doesn't care about time. There's no semantics of time. It just says, you give me a signal, I'll give you half of that signal back. Then we can think of this amplification block as a functor, or at least using a functor. So the input to the amplification block, which is our Morse code source, that's a time domain signal. And so if we represent time domain signals as a category, as distinct from non-time domain signals, or just sort of arbitrary streams of values, as another category, then we can imagine that there's actually a functor implicit here that's pulling things from one category to the other. So let's look at our amplification example. We have a time domain signal, that's our source signal that we need to amplify. And we have a non-time domain amplifier function, that's f of x. So our time domain signal is already in the time domain, so it's an object in that category. But our amplification signal, our f of x, is not in the time domain category. It's just a signal-to-signal function. So we actually need a functor to pull it over into the time domain signals category. And now it has the right shape to operate on our input signal. Does that make sense? Any questions about that? OK. So the takeaway here is functors are really useful for if we have multiple categories and we need something from another category in one that we're working with. OK, now let's talk about natural transformations. And this one's going to get a little bit in the weeds, so please let me know if you have any questions. So in category theory, a natural transformation is actually an arrow between functors. So let's try to visualize that. So here we have three categories, C, D, and E. And C is the only one with an object, and that object is X. So since natural transformation is an arrow between functors, let's first look at functors here. So I've added one functor F, which is a functor between C and D. So given an X, which is a C object, we can make an F of X, which is a D object, using our functor F. And now with a new functor G, which is a functor from the category C to the category E, we can take our X object and map it into the E category as a G of X. So now let's add a natural transformation. This natural transformation P, so again, we actually have, 5 categories here. We have category C, category D, category E, and then the category functors, in which functors are objects, and the category of natural transformations, in which natural transformations are objects. So we've added a natural transformation P, and that's an arrow from F, which is a functor, to G, which is a functor. So P is an arrow from between functors. And what that means is, if we have an F of X, which is a D object, which was produced by mapping F over X, we can convert that into a G of X, which is a E object produced by the G functor, using the natural transformation P. And then we can go in the other direction with another natural transformation, which is just an arrow in the opposite direction. So Q is a natural transformation from G to F, or it's an arrow from functor G to functor F. Is that clear? Enough? All right. Yeah, sorry. This is just ASCII, and it's by far the limit of my artistic ability. So hopefully, it still communicates effectively.
With the jargon language like this is that, in some senses, the concepts are ridiculously simple.
Mm-hmm.
And we need the jargon, we need words to be able
Right.
to understand what we're talking about.
Right.
But we get lost in it. I mean,
Yeah, and I agree. Yeah, I think before you're completely familiar with the jargon, you can get lost easily, which is part of the reason I like thinking in terms of these boxes and arrows, because I can really visualize the object moving around and what's moving it between categories. So in functional programming, natural transformations are usually a squiggly arrow like this, and in this case, they are a natural transformation would convert an f of a, where f is some type constructor, to a g of a, which is g is also a type constructor. So in this case, our categories are type constructors, kind of like we saw before, and our natural transformation is taking us between them. So just like we have f and g here, we had f and g here. It's the same thing.
One question on the natural transformations. Do
Yeah.
they require you to, for your functor to not be forgetful? It's like you have to map backwards from the functor, or is it just there's a transformation between the two functors?
So interestingly, natural transformations, at least in practice in functional programming, aren't defined in terms of functors at all. So, I mean, the underlying theory, possibly, I don't know, I'm a category theory beginner, so can't really answer that. But yeah, it is interesting that it's not defined in terms of functor, even though in category theory it's defined as an arrow between functors. And we're actually going to get into that a little bit. So here's an example, a concrete example, of a natural transformation between option and list. So this says, if you give me an option of something, I'll give you a list of something. And so it converts none to an empty list and some to a unary list. So as you point out, there's nothing on here about functors. But we've already defined a natural transformation as an arrow between functors. So we can actually sort of think about or imagine that there must be two implied functors that this thing is an arrow between. And if there are two functors, there's also must be some third category that those functors are pulling from to get us into option and get us into list. And that category might look like this. So just like we had before with C, D, and E, now we have the category of types, which is just simple types, int and string and so forth, where an A kind of corresponds to an option of A and corresponds to a list of A in these other categories. And so just like before, there must be a functor between these two. So in functional programming, as I said, the implementation of a functor usually has the same name as the type constructor. So like in Scala, option has map. So option is kind of its own functor. But it doesn't have to be that way, but sort of in practice, that's what we see. So here I just called the functor O, and O is a functor between the types category and the option category. So O, in other words, maps an A to an option of A, just like we saw before. And then similarly, imagine an L functor that maps an A to a list of A. And so now we can see that our option to list is starting to mirror what we already saw. And so we would say that option to list is a natural transformation from the O functor to the L functor. Okay, so let's look at natural transformations in the radio. But before we jump back into the radio, we're going to cover a little bit of theory first. So we've already seen that some signals don't have really any semantics. They're just a series of numbers, and that's like our f of x equals 0.5 times x. Other signals are values over time, so we say that they're in the time domain. Another way to represent signals is called the frequency domain. And to visualize that, I have this example. So in this radio, we have 4 sources. Each of these is a sine wave at a different frequency. So we have a 1 kilohertz sine wave. It's actually a cosine wave. 2, 3, and 4 kilohertz cosine waves. We're adding all those together, and then we're inspecting them. So this top chart shows each of those 4 signals. And so they're just 4 sine waves with different frequencies. And then the bottom, on the left, we have the sum of those 4 signals. So when we add 4 sine waves together, we get something that looks kind of like this. And that's over time. But a different way to look at that is to think of it in terms of frequency. So we know that we have 4 signal sources, and they each have a frequency, 1, 2, 3, and 4 kilohertz. we can plot that in a frequency plot like this. And these vertical spikes are just kind of a convention for how this is represented. But we can see that we've got a spike at 1, 2, 3, and 4 kilohertz, and their amplitude is 0 on a logarithmic scale, so that's a 1. And so the interesting thing here is that these two graphs are showing us the same information. It's just different ways of representing it. This says, hey, over time you've got this funny shaped signal, which is the sum of these signs. This one's telling us that, hey, over frequency you've got one sine wave at 1 kilohertz, one at 2, 3, and 4 kilohertz. Does that make sense, time versus frequency domain? Okay. Okay, so we can use that approach to actually build a digital filter. Okay, so in the top left, we have 4 blue spikes. Those are those 4 sine waves from before in the frequency domain. We also have this green signal, which is sort of a square wave or a rectangular wave. On the right, we have the frequency domain, and it's showing the result of multiplying this green signal by these blue signals. And the reason it's all 0 is because everywhere that the green signal has a value other than 0, the blue signal is 0. And then over here, everywhere the blue signal is non-zero, green is 0. So green goes down to the 0 and continues. So anything times 0 is 0, the output is 0. On the bottom left, we see our 4 source signals. That's not going to change. It's just to remind you that we've got 4 sine waves up here. And then the output, let's see. Ah, yes. So the lower right will be the time domain version of this one. So if we change the shape of this green signal, which we can do by expanding its cutoff, we start to get some output. And so what we're looking at here, we have 1 spike in our output that's in the frequency domain. And we have what looks like just a sine wave here in our time domain output. And what's happening is the multiplying these 2 signals together, green by blue, results in a single point, and that's where they're both 1 or both non-zero, and that's what propagates to the output. If we continue to expand that, excuse me, that square wave, we can start to cover more and more of the input. So now our output has these 2 values in it because that's the only place that the product is non-zero. And we can go on and on. We can keep including more and more signals under this thing. If we include all 4, then maybe. Then we get our original 4 spikes that we were looking at previously. So the reason that this is interesting and useful is, say we have a source signal with these 4 sine waves, and for some reason we only want the 1 kilohertz and 2 kilohertz sine waves to be in our output. We want to filter out the higher frequency ones. Then all we need to do in the digital signal processing domain is build a function that, when multiplied with the source, zeroes out those top 2 signals. And that's a filter. That's a digital filter. Okay, so now I think we can go back to the radio. So in our radio, we have this filter block that I mentioned, and that is actually exactly what it's doing. So if we drill down, we have our source coming in, and we have another signal here, which is just a square wave with kind of the right width that we're looking for. And we multiply them together and spit it out. But to do this, the signal coming into our filter block is a time domain signal. And this multiplication that we saw has to happen in the frequency domain. We have to multiply frequencies that we don't want by 0. And we can't do that with a time domain signal. So what we need to do is first convert our time domain signal into the frequency domain, then do the multiplication, then turn it back into a time domain signal so we can spit it out for use by the next block. And if you're curious, converting a signal from time domain to frequency domain uses something called a Fourier transform. And converting it back is an inverse Fourier transform, which is how these are actually implemented. Okay, so now we have this new domain. We can think of it as a category. So in our radio, we have 2 categories of signals. Really, we have 3, but I left the sort of undesignated signals off. So we have time domain signals. That's things that look like our sine waves. And we have frequency domain signals. That's those spikes over frequency. And our time to frequency conversion turns out to be a natural transformation, just like option to list. And similarly, our frequency to time conversion is also a natural transformation in the other direction. And so the takeaway is that I couldn't find a good term for this, but natural transformations convert values between types that were built with some type constructor. So if we have an option of something and we want a list of that thing, natural transformation is for us. Okay, so sorry, I kind of rushed through that. The takeaway here is that recognizing functional patterns is actually useful in places that we might not think it's useful. Behind the scenes, everything in this flow graph is really a functional program. It's a bunch of functions and a bunch of streams. But that's not necessarily apparent by just looking at this graphic. In addition, this gets compiled into Python code, and then some of the heavy lifting, like the Fourier transforms and the more computationally complex things, are written in C. So nowhere in any of this is types or type constructors or anything like that. But it's still really useful to think in terms of those things because we can visualize what's happening and understand how to manipulate it. So this talk was largely based on this paper, Categories for the Working Hardware Designer. And I really recommend that paper. It's pretty interesting. She uses category theory to design a hardware description language. So she's building VLSI circuits in a Ruby-based language that's all based on category theory. And then if you're interested in category theory in general, if you want to be a beginner like I am, this book by Pierce is really approachable. I had some trouble with books that are more meant for mathematicians because I am not a mathematician. And this one really covers it well. Everything that we've covered in this talk is on like page 1, but it's pretty good. And then if you're interested in signal processing, I recommend Owen's book. Are there any questions? Yeah.
I'll ask a question. So, like, if you had 2 people doing their one Morse code message, could we use the decomposition to be able to see those independent signals, to be able to separate them out?
Yeah, definitely. If there was some way of distinguishing them from each other. So, for example, if looking at our filter example, I mean this one. So if one person was transmitting a 1 kilohertz signal and another person is transmitting a 2 kilohertz signal, but they're on the same carrier maybe, so they would maybe sound like 2 different audio tones on the same frequency, you could use this approach to listen to just one of them. And that's how a lot of transmission lines work that way. Like in a fiber optic line, you have many, many, many signals all on that line, and they're distinguishable either like this in frequency or in phase or in some other way. And you can use approaches like this to take them apart and put them back together. Yeah, it's pretty much magic. And actually, interestingly, all these signals that we have, like this square wave and these spikes, are practically impossible. You can't actually make these signals because to make a perfectly straight square wave would take an infinite amount of information. It'd take an infinite number of sine waves added together. And it takes too long to compute infinity on my computer. So we can sort of pretend that this works, and you do the math, and out comes a signal. That does end up creating a bunch of aliasing and artifacts that we do need to filter out. But yeah, it's a really neat way to conceptualize.
That's not true on the hardware side, though, right? It's just software limitations.
Well, it's a side effect of the math.
The analog is better. The analog is better, you're right. Yeah. But it still has limitations. It's
It's a
not gonna be
differentiation problem, it's purely statistical.
How do you recognize a constructed type?
That's a good question that I don't have a good answer to. The question is, how do you recognize a constructed type? In functional programming, I would just see if the type came from a class that has one type variable. So the option class, which we have a slide for back here, I believe in Functor. Here we go. So option is declared as having one type parameter. So I guess I would look for a concrete type and see if it has a type parameter in the declaration. Yeah, the reason that's tricky is because an option of int, for example, is a type, just like int is a type. So you can, I mean, they both are defined as type. So like a constructed type isn't really a thing other than an informal understanding that it came from something that has a type variable in it.
At least in the Haskell world it is. If you look for just terminology of kinds, so kind is like the type of types. So anything in Haskell will see like star, arrow, star. It's like that's the type or the kind of like maybe your option.
Right.
Which is so it takes another type and produces another type.
Yeah.
So if you look for that terminology, that's what it's called, at least in Haskell.
Yep. Yeah, and all this is very hand wavy too. If you wanted to, you could define a different kind of category for maybe even higher kind of types if you wanted to, or for values instead of types. Basically, the sky's the limit. If you can think of the sort of nouns and then the arrows between those nouns, you've got a category.
Excuse me, switching over to the physical side of this, where we're almost cheating using natural transformation because we're dealing with signals.
Right.
What happens, they should be invertible, they should have all these nice mathematical properties. What happens when we can't deconfound them, where we have too much closeness or they weakly match the input function? Do these categories stay open? Something like a lazy list? Are they going to produce nulls? Are they going to just go, give you some noise back? In production, say if we don't have, the handler doesn't figure the signal, what happens?
Are you talking about in the radio example?
Yes. So like we built all these functions and we built this nice functional
Right.
composition structure. But say our like time to frequency is just giving us back noise. Will it fail on that? Will it provide? I suppose we could do that by convention. But.
Right. So this is more useful for constraining what you can do by type. But if the actual values at runtime are bad, that's a runtime problem. The reason this is useful is, despite the fact that it's really in Python and we don't have type constructors, when we are in a situation where we have type constructors, or if we at least have comments that say, hey, the type of this is such and such, this helps us make sure that we're operating in the right domain. So if we have a frequency domain signal, we don't forget and treat it as a time domain signal because our compiler prevents us from doing that.
Yeah, that really gets my question. Thank you.
Cool. Any others? Yeah?
And this is totally privileged, so can you talk about how you broadcasted the LambdaConf logo?
Yeah, I was wondering if that would come up. So here we go. So what we're looking at is the electromagnetic spectrum centered at 1 gigahertz, and it goes about 1 megahertz on each side. And it's a waterfall display, so time is increasing in this direction. So what we actually transmitted here was noise on these frequencies, and not so much noise here, and noise on these frequencies. And then after a certain amount of time, we changed the frequencies on which we're transmitting noise a little bit. And that's called spectrum painting. And yeah, you can, actually for GNU Radio and for this hardware here, there's somebody made a GitHub project where you can take any PNG file and convert it into what's called an IQ file that can be read directly into GNU Radio, and then you can paint whatever you like. But I wash my hands of responsibility of that because the legality is. What's that? Yeah, exactly. Yeah, I think. This is the repo that I used. I think it was done for like DEF CON or one of those conferences.
You just run this comparative, right? So
Yeah, exactly. So so the FCC has all these rules about how much power you can transmit and on which frequencies. If I made an image that had my call sign in it, then I could transmit that on one of the amateur bands and it'd be okay. It'd be kind of annoying though. So.
Can you talk just a little bit about the practical side of putting together some of the stuff in GNU Radio and what you do and how you do it?
Sure. So the whole point of software-defined radio is hardware is really expensive, and especially hardware that works at the frequencies that are useful in radio. So the more we can move into software, the cheaper it becomes, especially to change something. And so software-defined radio is mainly targeted toward those type of problems. And actually, I mean, everything in your cell phone is software radio. Well, not everything, but a big chunk of it. Like encoding the radio for the cell tower or Bluetooth or FM radio if it's got one. I don't know, there are definitely industry applications of GNU Radio, but I'm not involved in any of those. For me, it's just a hobby.
Yeah, no, I imagine you're just playing around, but so did you construct all the blocks yourself? Did you?
Oh, sure, yeah. So I guess a quick GNU Radio 101 is when you install and start it up for the first time, you get this big library of blocks, and it's got all kinds of, pretty much everything in this talk is standard. You would never really build a filter like I did. You would use the low-pass filter block, which has been written, in C, and it's very optimized and everything. And it doesn't use these terrible square waves that are impossible that I used. But yeah, you get most of what you would need out of the box, and then you can write your own blocks either by putting them together like this, or in C or in Python, and add them to your environment.
And if you stay under a certain amount output range, it's okay?
Yeah, I think unlicensed broadcasts, like on the FM band, for example, you'll have to look this up, but I think the FCC says as long as it's under a few microwatts, you're fine. And so, like your car FM transmitter that you get when you have an old car, that's what those operate at. So very little. This HackRF goes up to about 10 milliwatts, which is still very, very little, but that's an order of magnitude more than the FCC limit. So usually it's best to either transmit into a dummy load, which is an antenna that basically turns all the signal into heat, or get a license and get on one of the amateur frequencies and follow the laws there. A lot of interesting applications that people use this for are things like replay attacks on your garage door opener or your car, wireless key, things like that.
Thanks for sharing.
Yeah. All right. Thank you very much.